Okay, so course 3 of probability and statistics. I'll repeat beyond time because I start to recall, okay, so. Okay. So we have finished the previous session with this, okay? So my aim was to prove this relation that is okay, question B of the exercise 24 of the summer list, okay? I have to prove this equality that is called the Newton formula, okay? That is how to develop a plus b to the power n, okay? My idea was to use an induction in order to do this, because I have a property to prove for all n belonging to n star. During the previous session, we have initialized for n equal to 1 and proved that it was correct. And now we have to prove the heredity in the case of the induction, that is to suppose that what I have is okay for n, and to prove that it will be okay for n plus 1, okay? And we have seen at the end of the previous session that there is a link, of course, between what I want, that is a plus b to the power n plus 1, okay, and what I know, that is a plus b to the power n, and this is given by this relation here, okay? So we are going to start just now. I have the template of my proof, if you want, okay, and now I just have to compute and to end the results, okay? So let's do it together. So I use my hypothesis, okay, so I will copy a plus b to the power n that is equal to this one. It's my induction hypothesis. So I have this sum with two terms, okay, as this sum within n plus 1 terms, okay? So what we are going to do first is to develop this relation, okay, with this. So if I do this, I will obtain two terms. The term when I multiply by a and the term when I multiply by b. Okay, so if I multiply this relation by a, I have a here, and it will transform a to the power k into a to the power k plus 1, okay? The same holds for the other term, that is, if I multiply this sum by b, okay, I have to multiply by b this product, and so b will be transformed into b to the power n plus 1 minus k. Exactly what I write. Okay, so I develop. First term, the sum from k equal to 0 to n, cn k, a k plus 1, b n plus k. It is what happened when I multiply by a plus the sum from k equal to 0 to n, c n k, a to the power k, b to the power, excuse me, it's a minus here, n plus 1 minus k, okay? So I have to handle these two expressions. Okay? And keep in mind that what I want to prove, and I have to keep this in mind, is that a plus b to the power n plus 1 is what I want to prove now. It's the sum from k equal to 0 to n plus 1, c n plus 1 k, a k, b n plus 1 minus k. Okay, it's what I want to prove this. My aim. That is to prove this one when I replace n by n plus 1. Okay. So what can I do? So the idea will be to regroup the two sums, but in a correct way. Okay? I see that in the second sum here, I am happy because I have what here? I have a k b n plus 1 minus k. So something that looks like this term here. It is not that bad. So for the moment, I will keep it this way. For the other, but it's not the same thing. I have a to the power k plus 1 and b to the power n minus k. It's not what I want. So the idea will be to change my index. Okay? because here I have something to the power k plus 1, okay, I will change the index k into another one in order to transform this sum, okay, with terms that looks like this one, okay? So let's do it. So the idea is to work first with the first part of the equality. So what can I do? The idea for the first sum, okay, is to replace, I will write it this way, I will replace k plus 1 into k. You have in the prerequisite, okay, you have a part concerning how to compute sums and change of index, that is the analogous of change of variable for integrals, okay, is something that you have to be able to do. So when I say this one, in fact, it means that it's like I define a new index, k prime, to be k plus 1, okay? So it's exactly what we are going to do for the first sum. So if I define k prime equal to k plus 1, okay, I have k from 0 to n. If k is from 0 to n, k prime will be from 1 to n plus 1. Okay, so I write this sum here. So for the moment I write k prime, and at the end I will explain to you why I don't need it in fact. n plus 1, my cnk becomes cn k prime minus 1. A to the power k plus 1 becomes a to the power k prime. It's exactly why I have done this job, okay? And I have b to the power n minus k, k being equal to k prime minus 1, so I have b to the power n plus 1 minus k prime. So this is this first sum here. This one is this one. And I have to add the other one that I don't change, I don't touch for the moment. So just a remark concerning what I have said previously. Here, since it's the beginning, okay, I have given another name to the index. I call it k prime. But in fact, when you do a sum, whatever the name of the index, you can call it k prime, you can call it I, j, as you like, okay? So it means that in this sum, okay, I have k prime, but I can erase the prime symbol here because I don't mind about the name of my index. Okay? It's just a variable that I can name as I like. It's like, okay, when we are going to compute integrals, okay, the integration variable, okay, can be named as you want. X, Y, Z, whatever. Okay? So I have now two sums, and why I have done the job, I repeat, because here and here I have something that look like these terms here. Okay? So now we are going to regroup the two sums. But when I want to regroup the two sums, I have to be careful of the bound in the summation. Here I have a sum from k equal to 0 to n. Here a sum from k equal to 1 to n plus 1. And if I want to regroup them, okay, the sum has to be over the same set of indexation. And I see that what I have in common between this one and this one, it's from k equal to 1 to n. That's why I write the first part of the sum as the sum from k equal to 1 to n, cn k minus 1, ak b n plus 1 minus k. But if I do this, I miss the term for k equal to n plus 1. Okay? For k equal to n plus 1, yeah. Yes, and what is this term? Okay. For k equal to n plus 1, I have here cnn, that is equal to 1. I have a to the power n plus 1, and I have b to the power n plus 1 minus n plus 1, that is also equal to 1. So the term here for k equal to n plus 1 in the sum is just equal to a to the power n plus 1. this is the first sum. I write it as a sum from 1 to n plus the extra term. Okay? I do the same for the second sum. For the second sum, I will make appear the index from 1 to n, okay? But if I do this, I miss the term for k equal to 0. What is this term? For k equal to 0, I have c0n, that is equal to 1, a to the power 0, 1, and b to the power n plus 1. So I have b to the power n plus 1 plus the sum from k equal to 1 to n of c n k, a k, b, n plus 1 minus k. And why this is interesting? Because now I have two sums with the same set of indexation, and it's possible to regroup them, in fact. Okay, I have two sums that I can write into a single one. I continue here. So I have a to the power n plus 1. I have b to the power n plus 1. And now I have also a sum that is a sum from k equal to 1 to n of what? I have to do this one plus this one. I can put into factor this term and I obtain what? I obtain something like this, so we are going to write it below here. Plus what? The sum from k equal to 1 to n of cn k minus 1 plus cn k factor of a k b n plus 1 minus 2. Do you agree? I just regroup these two sums into a single one, meaning that I write a single sum with inside this one plus this one. That is exactly what I have written here, putting what they have in common into factor. Okay, so now a priori, when I see what I want and I see what I have for the moment, there is this term that is not present in this one here. But have a look on what we have done during the previous session. During the previous session, we have proved that we have this equality here. Look at me in the slides here. But we are going to use the fact that cnk minus 1, that is this term, plus cnk, that is this one, is just in fact equal to cn plus 1 k from the question A of the exercise 24 of the summer list. Okay? So let's write what I have at the end. I have a to the power n plus 1 plus b to the power n plus 1 plus the sum from k equal to 1 to n of cn plus 1 k, a k, b, n plus 1 minus k. And when I look at what I want, that is, I want to prove this relation here, but I have this general term that is the same as in this sum here. The only problem I have is that here I have a sum from k equal to 0 to n plus 1, while here I have a sum from k equal to 1 to n. But I have two remaining terms. And of course, what I can remark, that if I take in this expression here, k equal to n plus 1, what I obtain? For k equal to n plus 1, I obtain 1 here, a to the power n plus 1, b to the power 0. That is, I obtain exactly this one. For k equal to 0, c0 n plus 1, that is equal to 1, a to the power 0, that is equal to 1, and b to the power n plus 1, that is exactly this term. So it means that the sum I am interested in can be written as the sum from k equal to 0 to n plus 1, c n plus 1 k, a k, b, n plus 1, 1 minus k, and I have done the job by induction. Okay. So what I have done in this exercise, okay, it was in order to illustrate a little the induction reasoning, but also to remind you, okay, concerning what happened when I deal with sums, okay. And I repeat that you have a reminder in my website concerning how to do this. And something that is important because we are going to start today the notion of random variable. Next session we are going to start to speak about discrete random variable and to compute a lot of interesting quantities in the framework of discrete random variable. We are going to be able to compute sums. That's why I want you to be able to compute sums. When we will deal with continuous random variable, we will deal with integrals. Okay, but it will be, let's say, in 2 weeks. Okay, or in three sessions. Are you okay with this? And the main idea, that is in fact the only one after it's just techniques, is to remark this. How to pass from my induction hypothesis to what I want to deal with, and then computation. But that is not technical, okay? The only idea is to use in this expression here what I have proved previously, but that's why you have an intermediate question just before, okay? And then I obtain what I want. Okay. So we have proved, and from now on we will be able to use, okay, what we call the Newton formula, that is how to develop a plus b to the power. Okay? Questions? So I repeat that it's important for you to be able to compute sums. Here I have just developed and handle sums, not more. The only thing that I have used is this one, that is just my question small a in the exercise 24. So I have done the job. Question? Okay? In the question C, in fact, of the exercise 24 of the summer list, okay, you have, in fact, 2 relations that can be deduced from what I have proved now. Okay? So if you are okay, may I erase this part here? I erase. So what I am interested in now. I am interested in, okay, this sum, this one here. I want to prove that C0n plus C1n plus C2n plus Cnn is equal to 2 to the power n. I want to prove this relation, okay? If I write it compactly using the sum notations, okay, what I want to prove is that the sum from k equal to 0 to n of the C and k is equal to 2 to the power n, okay? It's exactly what I want you to prove in the statement here, this one. I write it using summation here. Do you have an idea to do this? And knowing that, it's the last question of an exercise, I can hope that I will have to use what I have done previously here. So I have this one. How to deduce this one? Yeah. So I have to make appear the sum of the C and k. If I have a look on what I have here, in order to obtain this sum, I can take A equal to 1 and B equal to 1, and I will have my result. Okay? So if I denote by star this relation, I say that here, just take A equal B equal to 1 in the relation star, and you have exactly the result. Sum of the C and k, that is equal to what? 1 plus 1 to the power n, that is 2 to the power. Okay? The sum of the C and k is equal to 2 to the power. Okay? Just a basic application of what I have proved previously. Second sum here. What is the difference between this one and this one? Here I have alternance between 1 minus 1, 1 minus 1, 1 minus 1, and so on. Okay? So instead of the sum of the C and k here, what I am interested in is what? Okay? So it's 1 minus 1, 1 minus 1, so I can write it this way. I am interested in this sum here. Okay? For k equal to 0, I have Cn 0. For k equal to minus 1, I have minus Cn C1 2, C1n, and so on. Okay? And my question is once again, I'll recover this one from this one. I'll recover this sum from this one. I have to take particular choices for A and B. What are they? So for B, I can take 1 to make it disappear, and for A, I just minus 1. Okay? Once again, I take B equal to 0 and A equal to minus 1. If I do this, I obtain exactly from this term my sum. And if I plug inside A equal to minus 1 and B equal to 1, I obtain 0. Minus 1 plus 1 to the power n is equal to 0. So you have exactly this. Question?
Just for the recording, B should be equal to 1.
Yeah, you're right. Of course, if I take B equal to 0, I obtain 0 here. Huh?
Yeah.
Okay? Except for K equal to n, but whatever, it's for sure B equal to 1 here. Okay? Thank you. So it means that from this formula that I have previously proved, okay, I can deduce some relation concerning the C and K. This one, for example. Okay. So this is the exercise 24. And we are going to continue with at least the beginning of the exercise 25, because it's something that we are going to use later on. So I will do the first part of the exercise 25, that is to compute this sum, and I will give you an indication in order to compute this one here. Okay. Do you have some questions? So here it's just to use several times what I have proved in the question B, taking particular values for A and B, because something I have proved before is true for any A and any B. Okay, so I have the right to choose A and B as I want, and I can deduce from particular choices these relations. Okay? I have this one. So here is something that is important, it's not the word, but something that is interesting in particular when we are going to compute later on expectations of discrete random variables. Something that I not define important for the moment, that will be defined next session, okay? But, so, I take the exercise 25 of the summer list, and I have to compute this sum here. So this sum that is not very different from the previous one here. Here I have the sum of the C and K, but here I have 0 times Cn0, 1 C1n, 2 C2n, and so on. Okay? So what I am interested in fact, here is what? It's the sum from K equal to 0 to n of K, C, and K. It's what I want to compute. That is okay, exactly what I have written here. And I write it using the summation notation. Okay? And I see that I have deduced this one from what I have proved in the previous exercise. Okay, I am not very far here. I have just a K before. So it should be possible, okay, developing what is the definition of the C and K to come back to the computation of this one. It's not what we are going to do, because I want to show you something that is more general and that can be applied, okay, in more general framework than this basic one. Okay? So that is from this sum, or from this sum to this sum, what I have to do, in fact, I have to make appear this K here. I have to make appear this K. Do you have an idea? So, my basis will be this one, what I have proved previously. Okay? I don't have k here, and I want it here. You take the logarithm. So be careful, so I know what you have in mind. If I take the log, okay, you have the log of a sum, and the log of a sum. It's not that bad idea. If you have this one only, yes, the logarithm of a to the power k is equal to k, the logarithm of a. Not a bad idea, but here, not that good because I have a sum here. And logarithm of the sum. Another one? Another idea?
We can derive a over k.
So the idea is that if you compute the derivative of a to the power k here, you obtain k to the power and k times a to the power k minus 1. So it's one way to do. So one way to write is just to say that here I can, it's a notation I introduce, I can denote it by f of a, this one by j of a. What are f and j? Well, in fact, f and j are polynomials, so I can compute the derivative at any order, okay? And we are going to see what happens. So I have the equality between two mappings, okay? I know that if they are equal, their derivatives will be equal. It's a notation. I have here something that depends on a. I call it, okay, so notation. Notation for this one and a notation for this one. In order to lighten what we are going to do just after, okay? So these two mappings defined from R into R are equal. So their derivatives are equal. So we have f prime of a that is equal to j prime of a. What is the derivative of this one? So a is my variable, b is considered as a constant. So I have something of the form u to the power n. Okay, the derivative of u to the power n is equal to n u prime u to the power n minus 1. So the derivative of f is just n, okay? The derivative of what I have inside that is equal to 1. And so I have a plus b to the power n minus 1. Here you have f prime, the derivative of this one. I repeat, my variable is a, b is a constant. And here I have just sums of terms of this form. The derivative of a sum is the sum of the derivative, okay, and I obtain the sum from k equal to 0 to n, c and k, k, a, k minus 1, b to the power n minus 1. Okay. And once again, so keep in mind what you want to do. What you want to do is to compute this sum here. How to make it appear using this part, my equality. What can I take in the previous equality to make appear the sum of k times c and k?
We are going to take AD equal 1.
Yeah? So once again, taking a equal to b equal to 1, I plug inside and I obtain what? N 2 to the power n minus 1, that is equal to the sum from k equal to 0 to n, k, c and k. You have exactly what you want. So what I want you to keep in mind from this exercise, it's not the value of this sum, I don't mind. But what interests me is that if I start from this kind of general expression, in order to make k appear, keep in mind that I can use the trick related to derivatives. I will use it other times in this course, okay, in the part concerning discrete random variables. And you will see that when we are going to deal next session with what we call the binomial distribution, but we will need this kind of computation inside in order to compute the expectation of such a random number. Okay? So I was able to compute this one. I want the same with k just before the c and k. My idea is to compute the derivative, because the derivative of a to the power k is equal to k to the time a to the power k minus 1. Okay? Do you have questions? So, if it's the first time you see this trick, I don't say that everybody has to be able to do that way, but now you have seen it. Okay? So to make a k appear something is not that bad to think about derivatives. So I won't do this one into details, but do you have an idea taking the same kind of tricks for this one? If I see the second part of the exercise 25 here. If I see the second part of the exercise 25, I am interested in what? So, once again, we are going to express this sum here using the summation notation. So, it's what I am interested in is the sum from k equals, so we are going to see just after, I have something of the form c and k over k plus 1. So it's the sum from k equal to 0 to n. Okay, it's exactly what I have written here, expressing it using this sum. So here, contrary to what happened in this case here, I don't have to make appear a k, I have to make appear 1 over k plus 1. To make appear my k here, I compute the derivative of this one. What was the idea in order to compute and to make appear 1 over k plus 1?
Integral.
Integral. Yeah. But you know that the primitive of a to the power k is equal to a to the power k plus 1 over k plus 1. Okay, so try to do it at home. In which way? You start from this one, okay, and you are going to compute, for example, particular primitives for each term. You have a classical formula for this one, a classical formula for this one, okay, so I give you just the idea, compute integrals or primitives. In this case, it is equivalent. Okay? Using exactly the same idea. Because I repeat why I do this, because when I have this expression here, the primitive of a to the power k is a to the power k plus 1 over k plus 1. So it makes appear the 1 over k plus 1 I am interested in. Okay? So do it at home and you have the correction in my list of correction in my website if you are interested. Okay, but the idea is exactly the same. The one that we are going to use in this course is more the part with the derivative in order to obtain a little bit later expectations. Okay? So if you don't have questions, okay, we are going to continue the course. I just check that everybody's okay, seems to work. I repeat, do you have questions? No? So it's easy for everybody what I have done? Well, let's say yes. But I repeat that your job is to ask questions, and mine is to answer. If you don't ask, okay, not possible for me to answer. May I erase?
Still again. This is the second place.
This is?
Just a second place.
Yeah? So now, what I have done previously. Previously, I have reminded what was the definition of probability. What is a probability? Okay. And we have dealt with conditional probability. Now, we are going to spend, okay, a few minutes concerning the notion of random variable. And in the next sessions, we are going to study more deeply particular cases of random variables. Before to give you the definition of what is a random variable, the technical definition, let's say I want to show you two examples of such a situation. But if I want to summarize using words what will be a random variable, I can summarize it like this. It's a mapping in the classical sense. It's a mapping depending on the outcomes of a random experiment. Okay? It's a mapping depending on the outcomes of a random experiment. So this is an intuitive definition. We are going to see an example of what I mean by this intuitive definition, and then we are going to see a definition that is a little bit more robust. Okay? So let's play a little, okay, to a basic game. That is this one. So now I can erase everything?
Yes.
Let's go. So we are going to see two little examples. Okay, one that is in the finite case and one that is in the case that is infinite and countable. So let's see what happens. So I am in the following situation. So it is example 1. I consider that I have two players, okay, A and B. So two players, A and B. And I suppose that we roll a fair dice, okay? So a fair dice is rolled, okay? Or is tossed. So it means, okay, that I have what I call the random experiment here. It's a classical dice. So what are my possible outcomes? 1, 2, 3, 4, 5, 6. So I have 6 elements in my universe here for the moment. And since I have a fair dice, okay, so we are exactly in the situation that I have previously introduced in order to introduce what is intuitively a probability. Okay? A fair dice means that below I have a probability in such a way that the probability of each outcome to occur is the same. And so here I have that for all I belonging to omega, P of I is equal to 1 over 6. Okay? Basic situation where I have a fair dice. Okay? So I roll a dice. That is a classical one that I suppose to be fair. And now let's see the rules of the game. Okay? So this is very basic. So if I obtain 1 or 6, I suppose that A will give to B €1. Okay? If I obtain 1 or 6, rolling the dice, okay, A has to give to B €1. Why not? Okay? If I obtain 2, 3, or 5, okay, B has to give to A €2. And at the end, if I obtain 4, nothing happened. So here my question is not to know if this game is stupid or not. Okay, if I am a priori B, I don't want to play this game. Okay, but whatever. Okay, so I have a random experiment, a little game. Okay, and we are going to let capital X be the profit of A. It is in fact the only one that has some interest to play here. Okay? So typically, if you have a little brother or a little sister, it's something you can play with him or her. Okay? If you want to have her or his money. Okay? So let capital X be the profit of capital A. So what is capital X? Capital X depends, of course, on what happened with the dice. So capital X can be seen as a mapping from omega into what? How many possible values for capital X? If I obtain 4, 0, my profit is 0, nothing happened. If I obtain 2, 3, or 5, 2, my profit will be 2. Okay, and if I obtain 1 or 6, I can say minus 1, it's a negative profit. Okay? So the set of the possible values here are minus 1, 0, 2. Okay? I have these three possibilities. My question is the following. What is the probability that X is equal to minus 1? What is the probability that X is equal to 0? And what is the probability that X is equal to 2? For minus 1.
1 over 36.
36?
Why
Why 36? I roll a dice one time, okay?
2 over 6.
Yes, I have 2.
1 over 3.
Yes, so I will obtain minus 1 in these two situations over the total number of possibility, that is 6. Okay, so it is 2 over 6, that is 1 over 3. Okay, the probability to lose €1 for A is 1 over 3. What is the probability of nothing?
1 over 6.
1 over 6. And what is the probability that X is equal to 2? Well, the remaining, if you want, but for the moment, you don't know, 1/2. Okay? If I do the sum of all these terms, I obtain what?
1.
I obtain 1. And it's nice that I obtain 1. Why? Because keep in mind that I start with an initial probability, that is the one related to the dice. That is, okay, the probability of each outcome is equal to 1 over 6. And now, I obtain in fact a new probability that is related to this mapping here. Okay, that is the profit generated by capital A if it plays this game. Okay, so I said the following. Defining, okay, for a new omega, that is omega prime equal to minus 1, 0, 2, Px of I equal to the probability that X is equal to 1. So if I define for omega prime equal to minus 1, 0, 2, this one, okay, for all I belonging to omega prime, we obtain the new probability. That is Px here. I obtain a new probability. So, what I have done here, but basically I have played a game that is something depending on randomness, a random experiment. I have built on this random experiment a mapping, okay, defined on the outcomes of my experiment. It has some particular values that are in this case -1, 0, or 2, okay, and in this way, if you want, I transport the probability that was a probability here, I transform it into a new probability on this set. A mapping that is able to transform a probability from a universe into a probability in another one, it's what we call the random variable. The new probability we obtain will be what we will call the distribution of this random variable. Okay? And when we are going to see the definition, you don't have to forget this, because it's what we do. So maybe in more abstract frameworks, okay? But always you will have a random experiment, a mapping, define on it, okay? And then you will be able to define the new probability from this situation, okay? So it was my first little example. And here I see that I am in a very basic example because I have only 3 possibilities for capital X, for the values of capital X. Okay? So I repeat that the relation with what we are going to do just after, that is the part concerning random variable, is that X will be what we will call random variable. Okay? And P of X will be what we will call the distribution of X. That is the new probability we may deduce from the definition of capital X. Okay? So a first little example. If you don't have question, let's see a second one with more possibilities for the values of capital X. Are you okay? Little game. You can change the game, okay? You will obtain a new mapping, okay? But with the same thing. Question, ask me the questions. Please.
What is it? X is having X is
No, just
distribution.
X is the profit. No, it's an intuition for the moment, okay? After you will have, okay, definition properly defined, okay, and so on. I just say that here I define capital X, the profit, okay? I compute these probabilities. I remark that when I do the sum of these 3 terms, I obtain 1. And I just say that I see that from my initial random experiment, that is rolling a dice, I can define a new probability on this set here, the set of the possible profit. I give it a name, but for the moment, whatever, I call it P of X, and I just say that I obtain a new probability. Later on, X will be a random variable, P of X will be the distribution of X. Okay? But it will be defined, I repeat, properly in few minutes. That's just a little example. Okay? Here. Another example. So I erase. I erase. Okay, so now I consider, so my first example was with the dice, this one would be with the coin. Okay? So I consider a fair coin. Okay? So I have 2 possible outcomes when I flip a coin. Omega is equal to head or tail, okay, so classical coin, okay. Then I suppose that, in fact, I don't need really that this coin is fair, so it's possible to suppose, but let's say an unfair one, in order to change a little. An unfair coin. Okay, it means that the probability to obtain head is not necessarily equal to the probability to obtain tail. So we consider an unfair coin. Okay? I will give a name to the probability to obtain head. I call it small p, and I suppose it to be strictly less than 1 and strictly positive. And what will be the probability of tail here? 1 minus p, because it's the complementary. And I give it a name. We are going to call it q. Okay? Notation of 1 minus p. So I have a coin, okay, that may be unfair. I denote by p the probability of head, and I denote by t, pt, the probability of tail that is denoted by q. Okay? We know. So, my situation will be the following. We flip the coin until the first head appears. So I flip the coin. If I obtain tail, I continue. I flip it again, and so on. Okay? So if you are unlucky, you are going to wait for a long time. Okay? With a probability that will be small. But it's possible to wait for a really long time if you are really, really unlucky. Okay? So we flip the coin until the first head appears. Okay? And I denote by x is just x is the number of times I have to wait for having the first head. Okay? So x is just the number of time I have to wait before having the first head. Okay, so it means that if x is equal to 1, it means that I obtain on the first horse directly head. If x is equal to 2, it means that I have obtained tail and head. If x is equal to 3, tail, tail, head, and so on. Okay? So what are the possible values? So of course x will depend on my random experiment, that is flipping a coin several times until the first head appears. Okay. What are the possible values for capital X? Well, it will be 1 or 2 or 3 and so on. Okay? So x belongs to n star, not 0. Because I have to do at least one toss, okay, in order to obtain it. Okay. What interests me once again is for all k belonging to n star, I am interested in the probability that x is equal to k. Are you able to tell me the probability that x is equal to k? So let's start by a basic example. So for k equal to 1. Okay. So k equal to 1, it means that I obtain head on the first. So what is the probability to obtain head? It's not necessarily 1/2. It's 1/2 if my coin is fair. If it is unfair, it's just p. Okay? This one, because it's the probability of head. And after I stop. What is the probability that k is equal to 2? If k is equal to 2, it means that I obtain on the first tail, on the second head. So when I said that I flip a coin several times, in general, the toes are independent. It's what we're supposed to have. Huh? Okay? I flip it another time, so there are no reason that there is a link between the first and the second toes. So it's the probability that the first is tail and the first is tail and the second is L by independence. It's the product of the probabilities. So I have probability Q to first obtain tail and the probability P to obtain L. So if I continue, what I will obtain as a general formula for the probability that x is equal to k. If x is equal to k, it means that I obtain for the k minus 1 first towards tail and then the head. The probability to obtain a tail is q. Times p. I obtain k minus 1 time the tail and then the head. Okay? So x will be in the following, what I will call a random variable, something depending on the random experiment. Okay? In the previous example, we have seen that when I do the sum of all the associated probability of this type, I obtain 1. Is it the case here? If I do the sum of all these terms here, that is, okay, if I am interested in the sum from k equal to 0 to plus infinity, because I have the values of k, q minus 1p, is this term equal to 1? Yes. The answer is yes, and my question now is why? So it's a... So not dealing with probability, just with analysis, how to compute this sum, let's say, and to prove that it's equal to 1 over p. Do you remind the way to do? So you have, or you add probably work before with what we call geometric sequences, okay? And you know that if you do the sum of the n first term of a geometric sequence, let's write it this way. What do you obtain? Do you remind the formula for this one? So that is just 1 plus q squared plus q to the power 3 and so on. You have a general formula for this one. Do you remind it?
1 over 1 minus q. Yeah.
So something like this. 1 minus q to the power the number of terms, that is n, over 1 minus q. And of course, if I want to write this, I have to suppose that q is different from 1. With what I have supposed here, q will be different from 1 because p is strictly positive. So if you don't remind this formula, possibility, okay? How to prove it? I want to do the proof, but I can give you an indication concerning the proof. So you have something to prove for all n. What can you do? No, before, just this one. For the moment, just this one. This equality here. After I will pass to the limit. Yeah, induction. I have a property to prove for all n. If I don't have the idea how to prove this one, you can prove it by induction. Proving it, okay, for n equal to 1, and so on. Very basic to do in 5 lines. Okay. So I have this one that is related, I repeat, to the sum of the terms of a geometric sequence. Okay. I am interested in this one here. Okay? I am interested in this sum. But this sum, if I do a change in index, okay, I can. So because you see that I have k minus 1 as an index here, I can change k minus 1 into k. If I do this, I will obtain a sum from k equal to 0 to plus infinity. So this sum may be written exactly in the same way. 0 plus infinity, q to the power of k, p. It's the same thing, changing the index, exactly as I have done in the exercise 25. Okay, so it means that I want to compute this one, okay, and it makes the link between what I have here. What is an infinite sum? An infinite sum is just, okay, when it exists, the limit of the finite sums. Okay, so if I have the right to do, when n goes to plus infinity here, this term converges toward the sum from k equal to 0 to plus infinity, q to the power k. That is exactly the term I am interested in here. Okay, and I just have to multiply by 1. For this one, what happened when n goes to plus infinity? It depends, okay? It depends on the values of q. But I am not in an arbitrary situation here. My q, since p is between 0 and 1, strictly the same all for q. So q is between 0 and 1. So what happened for q to the power n when q is between 0 and 1? It goes to 0. And this one goes to 1 over 1 minus q, that is equal to 1 over q. So this sum is equal to this one, that's why I have this one. Okay? So I repeat, once again, you have a situation with a starting point that is a random experiment, that is this one. I define a mapping depending on this random experiment. And then I just remark that I can define a new probability, the one that will be related to these quantities here. And I have a new probability because when I do the sum of all the terms, okay, I obtain 1. I obtain really a probability. So here it's another example of the preceding type, but where the set of my possible values is not finite, but countably infinite, in fact, okay? The sequence. Okay? But the idea of this little chapter, okay, is just to give general definition for this situation. Okay, so it will be a little bit more abstract than this one, but it's this one that you have to have in mind. Okay, when we speak about random variable, we always have in mind, okay, a mapping depending on the outcomes of random experiment. Okay? Even if it's not that clear in the theoretical definition. Okay? Do you have a question with my example? Okay? So I do exactly the same. I have this formula, and what I have done here is just remark that when I do the sum of all this one, I obtain 1. I want this one, but I obtain this one. Okay? And so, if I define Px of k by the probability that x is equal to k, for k belonging to n star, P of x is a new probability that I will call later on the distribution of capital X. Okay? If you are okay, we are going to start with the course now. And in the top of the first slides, okay, but you have the two examples we have spoken about, okay, now. Are you okay with what I have written on the board? If it's yes, I may erase. Yeah? Okay. Here you will have, okay, the very general definition of what is a random variable. Okay. So you have what? You start with the probability. Okay. with a set of definition that I denote by calligraphic A, but whatever. And this probability is defined on the universe omega. P of omega is equal to 1. So what I will call the random variable in this course, okay, will be very, very general. Okay? So for me and for you, so a random variable will just be a mapping from omega into R. Omega being the universe related to the probability P. So if you see my definition, you have a regular here. Okay, a regular. What is the meaning of this regular? In this course, since I have decided not to speak about sigma algebras, and so not to speak about what is in fact the nature of this calligraphic A here, regular will mean for you everybody. Okay? So any mapping will be a random variable. But just keep in mind that you will have to be in this situation. I have a probability defined on the universe. Okay? In my previous examples, it was the universe related to rolling a dice and the associated probability, or flipping a coin until the first head appears and the associated probability. And X is just a general mapping defined on the universe with values in R. Okay? Basically. Not more. So a very, very general definition that in fact is a little bit empty because I don't precise exactly what is this one, but for us, okay, you won't have to check that you won't have to check that something is a random variable. If it is a mapping from a universe into R, it will be. Okay? Just a little notation I introduce. What is the range of a random variable? That is in fact the range of a mapping. It is just the set of the possible values. Okay? I will denote by R of X the set of the possible values of capital X. In my first example, it was -1, 0, or 2, the set of the possible values for capital X. In my second example, it was n star, 1, 2, 3, and so on. Okay? The integers except 0. Okay. Very basic definition, and in fact nothing to say because my regular, okay, I suppose that it will be always fulfilled in this course because, okay, if I want to enter into the details, okay, I need to enter into the details of sigma algebra here, and it's not my purpose for this course. Okay? You will see this in the second semester. So let's see an example. So we have seen basic situation previously, but a little example that is a little bit more general. So in an exercise we have done together from the summer list, okay, I have defined the indicator function. Okay, if I have a set that is included in my universe, we have defined together what was the indicator function of A. The indicator function of A, okay, was a mapping from omega into 0, 1, such that it associates to any element of omega, 1 if double A belongs to A, and 0 otherwise. From my previous definition, I have here a random variable, a very basic one, taking only 2 possible values. Huh? Do you remind this? We have seen this in the first session. Huh? We have done an exercise on how to handle this indicator function. And from my very large definition here, I have here a random variable taking values, okay, in a set with 2 elements, 0 or 1. Okay? Very basic example of a random variable taking only 2 values. Okay? And I will come back on this example later on, okay, so that's why I give it here, because it will be an example also used, okay, in the next proposition or definitions. So indicator function, that is a mapping from my universe into 0, 1. That is equal to 1 when the element W belongs to A, and 0 when W belongs to A complementary. Okay? So it seems to be strange for you. Do you have some question? No, it's okay. I have already dealt with this definition. Okay. So what you will have to keep in mind, once again, so since I have a very, very large definition without precising what is this regular here, the interest is that you will be able to do what you want with random variables. You can do sums of random variables, and you will obtain a random variable. You can do products of random variable, you will obtain a random variable. You can do the compositions of random variables, and you will obtain random variables, and so on. So what you need to keep in mind is that with random variables, you can do what you want. Okay? It's not that strange to have this. So typically, when you do analysis, in general, you can work with, let's say, continuous mapping, and you know that the product, the sum, and so on of continuous mapping is a continuous mapping. Here, you will have exactly the same for this very basic definition. Okay? And even if I am a little bit more rigorous in the definition of what is regular here, I still have this thing here. That is, with random variable, we can do what we want. Okay? So we have an example here and two intuitive examples, okay, in what I have done previously. Okay. What we have remarked in the two first examples was that when I have a random variable, I define a new probability. It's exactly what we are going to see now. Okay? It's exactly what we are going to see now. Do you have some question on these slides? Okay? I continue. So proposition and definition. So we are going to first define what is the distribution of a random variable. And our jobs in the next sessions will be to see particular cases of distributions, binomial, Bernoulli, geometry, Poisson, Gaussian distribution, exponential distribution, okay, but all these particular cases coming from these basic definitions. And the distribution is exactly, okay, if you come back to my two previous examples, the new probability that naturally appears from the transform of my probability, my initial probability, using my random variable. Okay? So the definition is this one, and we are going to prove that I have a new probability. So that is when I define the things this way, I have a probability. And the name of this new probability will be the distribution of x. Okay. So I have my capital X, that is from omega into R. Okay? A mapping. Now what is the definition of a mapping? Someone able to give me a clear definition of a mapping? No? We talk about mappings, okay. What is a mapping? In one little sentence.
An operation to relate the elements of one set to the elements of another set. Some rule to relate the elements of one set to the elements of another set.
Okay, I agree with this. I am agree, but I will be a little bit more precise, just a little bit. A mapping is just something that transforms, or that relates, if you want, that transforms one element. So, in fact, each element in omega will be transformed, but will be transformed into a single element in R. So it means that you associate to any element here a real number, but a single real number, not 2, 3, 4, or 5. Okay? You have, and you will study maybe in the course of micro some kind of extension of mappings that we call the correspondence. And correspondence are what? Okay, things that associate to a single element here a set with possibly more than one element. But in the case of a mapping, one element is transformed into one element. Okay? Typically, you have here the graph of a mapping, because if I take an element here that is transformed into a single element here, this one is not the graph of a mapping. Because if I take an element here, you may have here 3 possible images here. Okay? So the mapping is something that associates to a single element another single element in capital R. Mapping is this one. Okay? Well, you want to be sure about what we are going to speak about. So I have my mapping from omega into R. Okay? And I define the following. I define P of X in the following way. It associates to any subset of R what the probability that X belongs to B. Okay? P of X associated to any B included in the real numbers for sure. Okay? The probability that X belongs to B. Why not? Okay? It's the definition given in the proposition. And my job will be to prove that this way I define a new probability that is defined on R, okay, with R as a universe. So before to do, okay, a little reminder before to do this. Okay, so I define Px this way. To any subset of R, I associate the probability that X belongs to. Concerning the notation, okay, so the set, the event X belongs to B. Just a notation for the following. It's the W belonging to omega such that X of W belongs to B. If it is what we call the pre-image of B by capital X. Okay? It is the point in omega such that the image belongs to B. Okay? So it's what we call the pre-image of B by capital X. Okay, and so you can use this notation to summarize this one, okay, but you can also use something you have probably previously used, okay, X minus 1 of B. Be careful, X is not bijective. X minus 1 is not the inverse, because I have no hypothesis concerning the fact that capital is bijective or not. It's just a notation for this set, the pre-image of B by X. Okay. What is interesting with the pre-image is that, okay, we have with the pre-image some very interesting and intuitive, okay, properties concerning the pre-image. What is the pre-image of the empty set? So it is X belongs to the empty set. Not 0. Empty set. Okay, that's what you have in mind. Okay, empty set. Because, okay, the W belonging to omega such that x of W belongs to the empty set. It's not possible to belong to the empty set, so I have no element. It's okay. So the preimage of the empty set is equal to the empty set. What is the preimage of all real numbers? It's the set of the W belonging to omega such that x of W belongs to R. What is this set? All omega. All of them have an image that belongs to the real number because x is a mapping from omega into R. So the preimage of the empty set is equal to the empty set. Okay, the preimage of, let's say, the new universe is the old one. Okay, and you have also this kind of nice properties here. This way, the preimage of a union and the preimage of an intersection. You remind the formula for this? I have told you that we have nice properties for the preimage. Okay, so what is the meaning of a nice property for these quantities if I want to compute them? We have the fact that the preimage of a union is equal to the union of the preimages, and the preimage of an intersection is equal to the intersection of the preimages. So you have this one. And this one. So you have these nice properties concerning the preimage of a set by a mapping. In some sense, okay, you can do anything you want, and you have also the following, the last one. X minus 1 of B complementary is equal to x minus 1 of B complementary. The nice formula. So be careful because it is true, these formulas are true because we'll deal with the preimage, with this definition. Okay, you know that when you have a mapping, you can also define the image of a set by a mapping. For the image of a set, you don't have such nice properties. It works for the preimage. Okay, it works for the preimage. If you are not okay with this one, you can try to prove them at home. How to do? By just coming back to the definition. What is the meaning of being in the preimage? I belong to the preimage if my image belongs to the set. And if you use this, you will have very basically all this relation. Just a little remark concerning the last one I have written here, this one. If you remind, okay, the slides I have given to you as prerequisite, so I have defined operational sets, okay, and when I have defined the complementary set, I have said that be careful because the complementary set of a set depends on my universe. If I change the universe, I change the definition of the complementary set. Here you have complementary and complementary here. But be careful because, okay, they are not related to the same universe. Why? Because the B is what? B is an element that is a subset of R. So by B complementary, I have in mind here R minus B, the elements that are in R and not in B. While here, x minus 1 of B is what? X minus 1 of B is a subset of omega. So here, x minus 1 of B complementary is omega minus x minus 1 of B. So these little symbols here and here don't make reference to the same universe. What I mean is this one, that B complementary is equal to R minus B, while x minus 1 B complementary is omega minus x1 minus 1 of b. Okay? B lies here as a subset of R, while x minus 1 of b is a subset of omega. Okay? So when I define the complementary set, just keep in mind that I don't have the same underlying universe. Okay? So what you will have to keep in mind is that when you have preimages, if you compute preimages of things that are classical operations on sets, but you have the good formulas. Preimage of a union is equal to the union of the preimage. Preimage of the intersection is equal to the intersection of the preimages. Preimage of a complementary set that is equal to the complementary set of the preimage, and so on. The preimage of the universe is the universe. Preimage of empty set is empty set. Okay? And I repeat that, in general, okay, it's what we see as the very, very beginning of a course of analysis, okay, in the first years. If you are not okay, try to prove, you will see that the proof is obvious and just coming from the definition of the preimages. Okay, so why introduce this? But because here, you have this term here. In fact, I can also write this one as the probability of x minus 1 of b. That's exactly what I have reminded here. Okay? And my job is to prove that I have a new probability, that px defined this way is a probability. Okay? What time is it? I do the proof now, okay, and I will do the break after. Okay. So, if I want to prove the proposition 7, I have to prove that Px defined this way is a probability. What is the definition of being a probability? What is the definition of a probability?
0 to 1.
0 to 1. So P of the universe has to be equal to 1. What is the universe here? R. Okay? So the first thing I have to prove, I'm agree with you, is Px of R is equal to 1. It's what I have to prove. Okay. Second point.
The union.
So, if I have a sequence of pairwise division set, the probability of the union is equal to the sum of the probabilities. Okay? What I have called the sigma additivity. So, Px of the union of the Bn is equal to the sum of Px of Bn if Bn the sequence of pairwise disjoint sets. Okay, so here I just remind the definition of what is the probability as defined, okay, in the first session of the course. So if I want to check that someone is a probability, I have to check that Px of the universe is 1, and that if I have a sequence Bn of pairwise disjoint set, the probability of the union, or Px of the union, is equal to the sum of the Px. Okay? And you are going to see that it's very basic to prove both, but having in mind what I have reminded on the preimages. Okay? That's exactly what we are going to do here to prove 1 and 2 in the case of Px, to prove that it is a probability. That will be a new probability that we will call the distribution of capital X, the distribution of the random variable capital X. So don't be surprised, it's exactly the definition we have seen together in the first class. After the intuitive definition I have given to you, I have given a theoretical definition that was exactly this one. Okay? So with pre-image and set, I can do anything I want. It's what I keep in mind. So I have the 2 points to prove. I have the 2 points to prove. For the first point, Px of R so what is Px of R? Okay, by definition, it's the probability of x minus 1 of R. We have seen together previously that x minus 1 of R is equal to what? Omega. This is equal to omega. And what is P of omega? 1, because P is a probability. We know that P is a probability. It was my initial probability. So 1, because P is a proba. And I want to prove that Px is a proba. Okay? But I know that P is. So Px of the universe is equal to 1. Okay? So secondly, I start from my sequence of pairwise division sets, and I am interested in Px of the union, where the Bn are pairwise division sets. Okay? So once again, what I can do first, I can use the definition of what is Px. Px is just the probability of x minus 1 of the union of the Bn. Okay? From what I have reminded concerning the pre-image, I have the nice formulas. The pre-image of the union is equal to the union of the pre-images. Pre-image of the union is equal to the union of the pre-images. So I can write the thing this way. P of this one. And now I have to conclude. So here, okay, I just use, for the moment, okay, I use the definition of Px, the fact that the pre-image fulfills some properties, some good properties in relation with the union or the intersection. So I have this. How to conclude? Do you have an idea? I know that P is a probability. So for any sequence of pairwise division sets, the probability of the union is equal to the sum of the probabilities. If I want to use this one, I have just to be sure that this one is a sequence of pairwise division sets. Okay? If I want to write that the probability of the union is equal to the sum of the probabilities here, since P is a probability, I have to check that x minus 1 of P is a sequence of pairwise division set or not. Okay? But to prove that they are pairwise different, if I take the pre-image of Bn and do the intersection with the pre-image of another one that I call Bp. Okay? I know that Bn is a sequence of pairwise division sets. That is, if n is different from P, Bn intersected with Bp is equal to the empty set, because Bn is a sequence of pairwise division sets. What is the intersection of preimages? I know from what I have reminded before that intersection of preimages is the preimage of the intersection. So this is the preimage of Bn intersected with Bp. But what is this one? Bn is a sequence of pairwise disjoint set. So what is Bn intersected with Bp? Empty set. And what is the preimage of the empty set? Empty set. So I can say that x minus 1 of Bn is the sequence of pairwise disjoint sets. And why I want this? Because now I know that the preimage by x of the Bn is a sequence of pairwise disjoint set. So the probability of the union is equal to the sum of the probabilities. Because P is a probability. So when I have a sequence of pairwise disjoint set, the probability of the union is equal to the sum of the probabilities. And it's finished, because what is Px minus 1 of Bn? Px minus 1 of Bn is just sum and Px of Bn. So you have proved both that Px of R is equal to 1, and that when Bn is a sequence of pairwise disjoint sets, Px of the union is equal to the sum of the Px. And so that Px is a new probability that we will call from now on the distribution of capital X. Okay? Let's do the break. Okay, so I continue with the course. And here I will define what is the notion of independence between random variables. What we have already seen together, we have seen the definition of independence between two sets. Okay? So I remind you that two sets A1 and A2 are independent if, what is the definition? So of course I need to have an underlying probability, that is capital P here. What is the definition of independence for sets? No. No. But if I have pairwise disjoint, it's to be pairwise disjoint. Independent is to be independent. Pairwise disjoint means that the intersection is empty. Here I have only two. So pairwise disjoint means they are with an intersection equal to empty set, but it's the probability of the intersection that is equal to the product of the probability. Okay? So in general, it's a thing that has nothing to do with to be disjoint. Okay? And typically, you see that if you are independent and disjoint, it means that at least one of them has to be equal to 0, because the probability of the intersection in the case where they are disjoint is 0. So this is to be independent for sets. Okay? We are going to generalize this definition in the case of random variables. Okay? So I consider two random variables defined on the same universe, x and y. And we say that x and y are independent if and only if for all b and c, the probability that x belongs to b and y belongs to c is equal to the probability that x belongs to b and the probability that y belongs to c. So you see that there is a link with this one. We have the probability of an intersection that has to be equal to the product of probabilities, but in fact it has to be okay for any preimages here. Okay? So in other words, okay, if I want to rephrase this definition here using the definition of independence between sets, I can say the following. So the notation of independence will be this one, as in the case of sets. Okay, the orthogonality symbol, the one I introduced at the end of the definition. X and Y are independent if and only if for all B, for all C, okay, included in R, I have X minus 1 of B that is independent of Y minus 1 of C. It's exactly what I have written here, that the probability of the intersection between the preimages is equal to the product of the probabilities. Okay? So to say that two random variables are independent just means that all the associated possible preimages, that are this one, are independent in the sense of sets. Okay? So it's just an extension of what happened in the case of sets. And for random variable, it has to work for all possible preimages. It's exactly what I have written in the definition. Let's see a little example to convince you that we have really an extension of this definition when I do this. Okay? So what is a little bit complicated a priori when I have to prove this one is that I have to prove for all possible preimages. And you may have a lot of preimages. Okay? So we will see in other situations that we will have tools in order to prove independence, that is without to check this for all preimages, but at this stage is the beginning definition. Okay? So let's suppose the following example. We are going to consider two indicator functions. Why not? Okay, it's my example. So I consider the indicator function of A, that is from omega into 0, 1, remind, okay, and the indicator function of B, from omega into 0, okay? So, I want conditions on A and B, in fact, to make these two indicator functions independent as random variables. Okay? So if I am interested in the independence of these two indicator functions, okay, my first question is what are all the possible preimages? Okay? So if I consider, okay, so just maybe change just a little my notation. I will take A1 and A2 here in order not to make confusion with my B that is here. Okay? So A1 and A2, I have two indicator functions. I want condition on the sets A1 and A2 to make them independent as in definition 10. My first question is what is the preimage of a set by the indicator function? So keep in mind that I come back to the definition. This is the set of the W belonging to omega such that the indicator function of A1 of W belongs to B. Okay? It's the definition of the preimage. I said that, in fact, in this very particular situation, I have just a finite number of possibilities to be a preimage. Why? Because the indicator function is a mapping with values in 0 or 1. So I have only two values. Okay? And I said that this fact implies that the number of possible preimages, okay, is finite and in fact equal to 4. Why? Because I have four possible situations. The case where 0 belongs to B, 1 belongs to B. The case where 0 belongs to B, 1 doesn't. 0 doesn't belong to B. 1 belongs to B. And 0 doesn't belong to B. 1 doesn't belong to B. B is a subset of R, and I have only these four possibilities. 0 is in B or not, and 1 is in B or not. So I have a total of 4 possibilities. What happened in the first case? If I am sure that 0 is in B and 1 is in B, what is the preimage of Excuse me, yes, this one. What is the preimage? The universe, yeah. Because it means that I will have everybody inside. All the possible values. So the indicator function of any element belongs to 0, 1. So the preimage of B by the indicator function of A1 is equal to omega. What happens if 0 belongs to B and 1 doesn't? What are the elements of omega with a value equal to 0 in fact? Not empty set. Because I can take 0 as a value. I can take 0 as a value if I am in A1 complementary. A1 complementary. Because it's the case where my values are 0. Okay? So the preimage of B, if 0 belongs to B and 1 doesn't belong, is equal to A1 complementary. What happens if 0 doesn't belong and 1 belongs to? What is the preimage? A1. A1 in the third case. And finally, if no possible values belongs to B, what is my preimage? Empty set. You have here the set of all possible preimages in the case of an indicator function. Okay? So what is the set of the preimages here? Well, by what I have written here, you have omega, A1 complementary, A1 empty set, okay? And then, for this one, you will have omega, A2 complementary, A2, and empty set. So, the two random variables will be independent if and only if anytime I take an element here, it is independent of an element here. Okay? But we have seen a condition together. So I don't know if I have the slides of the previous class. Maybe not here, but whatever. What we have seen together when I have introduced the definition of the independence between two sets. I have said to you that if A1 is independent of A2, I have A1 that is independent of A2 complementary. I have A2 that is independent of A1 complementary. I have A1 complementary that is independent of A2 complementary, and so on. You don't believe in me? I just show you that we have done the job together. So where are the slides? Somewhere here. So where are they? It was here in the first station. I remind at the end. Proposition 5. If A and B are independent, A complementary and B are independent, A and B complementary, and complementary and B complementary. Okay? And so, if you have understood what I have said here, in the case of indicator function, I can write it this way, indicator function of A1 will be independent of indicator function of A2. If and only if, do you have a basic assumption in order to ensure this? Well, since I have only these possible preimages for indicator function of A1 and these possible preimages for indicator function of A2, simply in this case, if I have the independence between sets, I will have the independence of the indicator function considered as random variables. Okay? So you see here that the notion of independence between sets is a real subcase of the independence of random variable, because in the case of very particular mappings that are indicator function, it coincides with the definition of the independence between sets. Okay? So in the case where you have this very, very basic random variable, to prove that they are independent in the case of my definition here, that is this one. In the case of my definition, that is to prove that all associated preimages are independent. In the case of indicator function, if you have the independence between sets, you will have necessarily the independence of the indicator function considered as random variable. And the argument is, I repeat, because I have here the set of the possible preimages that is very restricted and just, okay, equal to this one and this one. Okay? So a priori I have to check that I have 16 possibilities a priori to check in order to prove the independence between the two random variables, because I have to take one preimage here and to take one here. So I have 16 possibilities to do. But from the little proposition 5 of the course, okay, I know that if I have the independence between the set L1 and L2, necessarily I will have the independence for all of them here. Okay? So just to say, I repeat that indicator function of random variable is just an extension of what we have seen in the case of sets.
Sorry, because I'm not sure if I understood correctly.
Yeah, tell me.
I'd like to show that every single set, if we look at the preimage,
Yeah.
those two indicator functions is independent from each other to show that this probability is independent. But
No, I don't speak about independence of probability here.
yeah, okay, but
No, not but. We have independence of set and we have independence of random variable. It's the only thing
Yeah.
that I have defined.
yeah, but how is omega independent from omega?
Let's write it. What is this? Omega intersected with omega is equal to 1. I have this because,
yeah, okay, makes sense.
in fact, the only cases that are interesting is the one related with these two and these two, and you prove that it works by the proposition 5. For the other, it is sufficient to write the same for the empty set and the empty set. You obtain 0 that is equal to 0 times 0.
So it's
Okay.
this is to prove only A1 and A2
Yeah.
independent.
So in fact, I repeat, I agree that you have to take 1/4 here and 1/4. You obtain 16 possibilities. But the only one that are a little bit interesting is the one involving this one and this one that are a consequence of proposition 5 we have previously proved. Okay? So independence between indicator function is the same as independence between sets. Okay? But of course, for more complex random variables than this one, you will have to do more to consider all the possible preimages that may be tricky to find in some examples. But don't worry, because in few sessions we will have, okay, more tools in order to prove independence of random variables that are easier to check than to consider all the possible preimages and so on. Okay? We will be able to check this on the probability mass function in the discrete case. We will have the possibility to check this on the joint density function, okay? And we will also have, okay, what we call moment generating function in order to check this in a very efficient way without being able to check the definition for any possible preimages. Okay? But my little example here was just to convince you that independence between random variables is just a little extension of what I have previously introduced in the case of sets. Basically. Okay? Through the notion of preimages. Questions? Okay? Next slide. Basic definition here. So may I erase the board? Okay? So in fact, at this stage, okay, so I have two parts in my definition. For the moment, I will use just the first one. The second one will be more related to the statistical part of the course. Okay? So I have a random variable x, so I have a probability from A into R, into 0, 1, excuse me. I have x, that is a random variable, this way. So probability, random variable. And I define what we call the distribution function. Okay? So the distribution function f capital X being related to my random variable here, is a mapping, okay, from R, in fact, into 0, 1, that associate to any real number the probability that X is less than small x. It's what we call the distribution function of capital X. Okay, the probability that X is less than small x for any real number X. Okay?
Complex is for random variable.
Hmm?
Is the complex remark for
No,
the
no.
variable?
My capital X is this one. Okay? I fix capital X in the statement. I define the distribution function of capital X here. For any random variable, I can define its distribution function. Okay? Let's see an example. I have on the board a particular random variable that is the indicator function. So let's see what is this mapping in the case where x is equal to an indicator function. So what happens in my definition if I take for capital X the indicator function of A of a set? Okay, I have said that it is a random variable, okay, and I want to, in fact, to represent graphically this one. So I can do this kind of picture, okay, my set of definition is whole R, and my values are between 0 and 1, okay? I want to do the graph of the distribution function related to my indicator function. So I am interested in the probability that the indicator function is less than small x. And I want to compute this for any small x. Okay? In fact, I say that I have only 3 situations. Only 3. What are the possible values for my indicator function? 0 or 1. So, first thing, what happens when x is strictly negative? What is this probability? What is the probability that an indicator function is strictly negative, in fact? 0. Because my indicator function take values in 0 or 1. So it means, I have some colors maybe, yeah. It means that when I am strictly negative until this one, okay, my value is 0. Here, I plot this one. Second case, so I have 0 here. Second case, what happens if x is positive or equal to 0 and strictly less than 1? When my indicator function is positive in the large sense and strictly less than 1. My indicator function takes values in 0 or 1. When it takes the value 0, it takes the value 0 when I am in A complementary. So my indicator function will be positive in the large sense and strictly less than 1 if this one is equal to 0, that is when the argument belongs to A complementary. So the probability that the indicator function is less than x in this situation is the probability to be in A complementary. So here my value is simply P of A complementary. So I can plot it here. Imagine that P of A complementary is equal to this one between 0 and 1. Okay, you are equal to this one. The last case, if x is greater or equal to 1, what happens? For my probability, but the indicator function is always less than 1 because it takes values in 0 or 1. So it is always less than small x in this situation. And so what is my probability? It is 1. And you have this one. So you have here, in the example of an indicator function, what is its distribution function? Here I take only 3 possible values because I take 2 values as a random variable, 0 or 1. Okay? So here I have plotted what is the distribution function of an indicator function in this situation. Okay? So on this graph, okay, I can see a lot of characteristic properties, in fact, of a distribution function we are going to see in the next slide. The limit in minus infinity, 0. Limit in plus infinity, 1. I see that I am increasing, okay, in the large sense. I am increasing. Not strictly increasing, because I have this flat part here, but increasing. And I can also see, okay, more technical properties as this mapping is in fact right continuous. If you take the limit, okay, of a decreasing sequence, the images will converge toward the good limits. I will come back on this point just after, okay? But I see increasing particular limits, okay, and so on. And in fact, these characteristics are typical from a distribution function independently of the fact that is the indicator of the distribution function of the indicator function or not. Okay. So I have this. Why not? Second definition, in my definition 11 here. So you have here basically the definition of the distribution function, and you have the definition of what we called the TOS. So tau, the Greek letter, tau, quantile. The TOS quantile. What is this? I define the definition. It's defined this way: Q of tau, that is the minimum of what? Of the x belonging to R, such that the distribution function of capital X at the point x is greater than 2. So what is this? The TOS quantile here is the minimum of the x such that the distribution function is greater than 2. Why not? Okay? And 2 is just an element in the interval 0, 1. So have a look here, for example. If I consider a tau being here, I take, so my tau is between 0 and 1, okay? I suppose that my tau is here. What is the minimum in my situation here of the x, such that the distribution function is greater than tau? What is the tau scantile here in my case of indicator function? The minimum of the x such that the distribution function is greater than tau. So, I take my x, here I am not greater than tau, I am not, and here I jump and I am greater. So the tau scantile in this case is equal to 0. Okay? If I take tau to be here, for example, what will be the tau scantile in this situation? 1. Okay? And you have the two cases, 0 or 1 in this particular situation. And why this one is well defined? In fact, it is well defined because I know that the distribution function is an increasing mapping, okay, that is between 0 and 1. So I am sure that I will be greater than tau one time, okay, if I take tau between 0 and 1 strictly. And I will be sure that I will have a minimum because I am increasing. So I will be less, and one time I will be greater, and after I will be greater. In the case you take tau equal to 1/2, it's what we call the median of the random variable. But I will come back on this point, okay, in the statistical part. Okay. So for tau equal to 1/2, okay, you have what we call the median of a random variable. That is the value that separates the values of the distribution function in two parts, the ones that are less than 1/2 and the ones that are greater than 1/2. The one, okay, so that the probability to be less is 1/2 and the probability to be greater is 1/2. But focus more on the distribution function today, because for the second one I will come back on this point in the slides concerning the statistical part of the course. Okay? So you have the definition of the distribution function. And we have seen together here an example in the case of the indicator function. I remind that in this particular example I have seen some properties, limit in minus infinity 0, limit in plus infinity 1, something that is increasing with some property. Okay? And we have the next proposition, but that tells us in fact that what I have remarked on this little example is in fact totally general. So, excuse me. This one, that will be the last slide for today. So some properties of the distribution function. So I just keep the definition on the board and we are going to prove some of them, okay? And for the one that I won't prove today, you have the proof of this proposition, okay, in the list of the proof that you have on my website. Typically, even if it's not that complicated, I want to do the proof of 4, 5, and 6. And 4, 5, and 6 are just in fact a consequence of a result we have seen in the first course. That was the following. We have seen together that when I have an increasing sequence of sets, the probability of the union is equal to the limit of the probabilities. I have said also that when we have a decreasing sequence of sets, the probability of the intersection is equal to the limit of the probabilities. These two statements may be used in order to prove that 4, 5, and 6 are okay, and you have the complete proof. I repeat, in the document on my web page where you have the proof of the proposition that I want to do in class together. Okay? We are going just to prove the three first ones that are very basic ones. So I just keep the definition on the board. We are going to prove the three first. So this proposition tells me that the distribution function is between 0 and 1. So for this one I don't have to prove, because in the definition itself of the distribution function I have a probability. The probability is between 0 and 1. So I am sure that the first one is fulfilled because f capital X of small x is a probability, so it is something that is between 0 and 1. So for the first point, okay. I don't need a proof. It is just from the definition. Okay. So let's prove that f of x is increasing. Right? Not necessarily strictly increasing, but increasing. So to prove this, what I have to prove? I have to prove that if x1 is greater than x2, I have to prove that fx of x1 is greater than fx of x2. I have to prove this. Okay? And I am in this situation. I have x2 that is here, and that is smaller than x1. Okay? So if I am in this situation, can you compare these two sets? I said that one is included in the other. I am in this situation with x2 that is less than x1. And my question is it possible to compare these two sets? I said that one is smaller than the other one in the sense of inclusion. Which one? This one is included in this one? Of course, I have this. Why? Because if I am less than x2, I am less than x1. So x less than x2 implies x less than x1. Okay? And in fact, it's finished because what we have seen together in the first session, we have seen that if A is included in B, P of A is less than P of B. So from this inclusion, I am sure that the probability that x is less than x2 is smaller than the probability that x is less than x1, because this set is the biggest in the sense of inclusion. And we have proved that the probability is an increasing mapping in the sense of inclusion. And what is this one? It is just the definition of fx of x1, and here just the definition of fx of x2. So starting from x1 greater than x2, I have proved what I want. So f capital X is an increasing mapping. Okay? It's a mapping that is increasing. x1 greater than x2 implies the image of x1 is greater than the image of x2. It is the definition of being increasing. Now keep in mind that we have seen in the case of the indicator function that we don't have in general the fact that I am strictly increasing, but I have just to be increasing. Okay? Just coming back from the definition. Are you okay with this one? Just use the fact that if A is included in B, P of A is less than P of B, and I use the definition of the distribution function. For the 3, I want to prove that the probability that X is strictly greater than A and less than B is equal to fxb minus fxa. So I have my B that is strictly greater than A in the third point. And I want to prove the relation in the statement 3 of the proposition 8. So what can I say? Well, in fact, I have the following. I said that if I take this set, so the set where X is less than B, strictly greater than A, and if I do the union with X less than A, what do you obtain? It's a disjoint union, in fact. What is this?
is less than B, less or equal to B.
I have this one. Okay? Just say that if I am in this situation, if I am less than B, two possibilities, I am here or I am here. I am less than A in the large sense, or I am less than B and strictly greater than A. Okay, basic relation. And now I can take the probability. I can take the probability. I have the probability that X is less than B. That is equal to what? I have the probability of a disjoint union. The probability of a disjoint union is equal to the sum of the probabilities. It's a finish, in fact. Why it's finished? Because by definition of the distribution function, I can write this way. fxb, here, probability that x strictly greater than A, less than B, plus fx of A. And you have exactly the third point in the proposition 8. Okay? I just use here the fact that the probability of a disjoint union is equal to the sum of the probabilities. So for the other point here, yeah.
Just to be sure, this weird sign, it's this joint union, right? Oh, yeah, this one. Yeah.
Disjoint union.
Okay.
Okay? And once again, it's something that I have defined in the prerequisite slides. Okay? That's why I use it. It's a union where here the two elements have an intersection equal to the empty set. Okay? In other words, if I use the language of this course, you have these two sets that are a partition of this one. Okay? Union is equal to the whole, intersection is empty. Okay? So when I write this one, you have a union without knowing if it is a union between disjoint set or not. When I use this symbol here, it means that it's a union, but between disjoint sets. Okay? So I have done the proof of the tree first here, and I repeat that you can also prove that the limit of the distribution function in minus infinity is 0, as we have seen in the case of the indicator function. The fact that its limit in plus infinity is 1. The fact that it is right continuous. What is the meaning of right continuous? Let me remind this. You have f from R into R. Okay? F continuous. You can express the continuity in this situation using sequences. Okay? Continuity. So C0 means continuity. Means that anytime I take a sequence xn converging toward x when n goes to plus infinity, then f of xn converges toward f of x. The sequential definition of continuity of a mapping. F is continuous if and only if, in this situation, when I have a sequence xn that converges toward x when n goes to plus infinity, f of xn converges toward f of x. Okay? The definition of right continuity is not that different. The only thing you have is that the convergence has to be particular, in the sense that xn converges toward x when n goes to plus infinity, and xn decreasing Okay, so you want to have a decreasing sequence converges toward x this way, then f of xn converges toward f of x. Of course, if you are continuous, you are right continuous. Because if you are convergent and decreasing, you are convergent. Okay? But right continuity implies that the sequence decreases toward x. And typically, if I come back to the case of my indicator function, previously seen together, you have the distribution function of the indicator function of A. We have seen together that you have something that take the value 0 when I am strictly less than 0, then P of A if I am equal to 0 or strictly less than 1, and finally 1. Okay? But you see that in fact you are not continuous from the left because you have jumps here. When I approach this one here, you have a jump after. So you are not left continuous. The same all for this one, the jump. But in this situation, since this point is included in my interval, okay, I have the right continuity. So if you take a decreasing sequence, it works. If you take a sequence that is increasing, it doesn't work in this situation because I have my jumps. So you have here an example of a mapping that is right continuous, but that is not continuous. Okay? So this is here a typical example of something that is right continuous and that is not continuous. Okay? And here, for a distribution function, I have only the right continuity. And you will have the proof, okay, if you are interested in the list of the proof of the course. So the limit, right continuity, and another result that we will come back on next session, but it's the way we define the distribution function, in fact. I said that the distribution function characterizes the distribution function, the distribution of x, as we can imagine by its name, distribution function. The distribution function characterizes the distribution of x. What is the meaning of this one? It means that if you have two random variables with the same distribution function, they are the same distribution. Okay? In other words, if f of capital X equal to f of capital Y, then P of X is equal to P of Y. Okay? So I don't enter into too much detail for this one because I will come back on these points, okay, in the next session when we are going to work with discrete random variables. But the last point tells you that if you want to characterize the distribution of a random variable as something that we want to be able to do and we want to do computation related to it, okay? But to know exactly its distribution or to know its distribution function, it's exactly the same. It's totally equivalent. Okay? So I will finish on this concerning the course for today. And the objective of the maybe 6 or 7 next sessions, okay, will be to study more deeply the case of what we call discrete and continuous random variables. The one, no, I don't have finished the course, huh? I finished the course, but we are going to do exercise, it's not the time, huh? Okay? I start at 1, I finish at 4, okay? Okay, so I close the slides. I take the list 3 of exercises and maybe you can try to do by yourself the exercise 6. I give you 5 minutes to do and in these 5 minutes I will check for attendance. Okay, so we do the exercise 6 of the list 3. This one. So let's say that one side is obvious and the other one is a little bit less obvious. You see this like this. So which side is obvious? No side? Yeah, this one is obvious. Why? Because but I know that A intersecting with B, by definition, is included in A and is also included in B. And I know that the probability is an increasing mapping. In the sense that if one set is included in another one, the probability of the first is less than the probability of the second. So I can deduce from these two inclusions that the probability of the intersection is less than P of A and less than P of B. So I can say that it's less than the minimum between P of A and P of B. I want to have the best bond, I choose the smaller one between P of A and P of B. And what I have in my statement, P of A is equal to 3 over 4, P of B is equal to 1 over 3. The minimum is 1 over 3. Okay? It's just by using the fact that the intersection is included in each set, so the probability of the intersection is less than the probability of each set. And so I take the smallest number, that is 1 over 3. Okay? And I use nothing here, no independence, no inclusion or no what, okay? I have this. So it was the easy side, let's say. Do you have an idea for the other one?
Can they intersect in one element? This one.
No. I repeat. It's not possible for you to take a particular case. I want you to prove this in Greek generality. So if you show me a little picture of a particular situation, if you are able to prove this, nice, but know what I want. I want the result in its Greek generality, that is without any kind of hypothesis on A and B. The only thing you know is that P of A is equal to 3 over 4, P of B is equal to 1 over 3. That's all. Okay? So just speak louder because I don't understand. So show me, maybe. Where is it? Yeah.
Yes, I can solve the code and I use the isopore.
Yeah, it's in the
It's enough.
Okay, if you want. It will work. It's not the way we do, but it works. So one possibility, okay? One possibility is to use this equality here, this one, so that A is equal to A intersected with B, disjoint union with A minus B. Okay? That is just equal to A intersected with B complementary, this one. Okay? You know what is P of A. For this one, you can use exactly the same idea as the one I have previously used. That will be this one will be less than P of A, the minimum between P of A and P of B complementary. You know P of B complementary, that is 2 over 3. And it's one possibility to find the solution. Another way to do this would be my way. Just when I see this statement, in fact, what I am thinking about. I said that, okay, I have in my statement A, B, and A intersecting with B. Okay? And I said that among the properties we have seen together, there is in fact, a priori, a single one where these three quantities are involved. It is this one. The fact that P of A union B is equal to P of A plus P of B minus P of the intersection. So of course my idea is not that away from R, because if you remind, in order to prove this one, I use this. So it's just two equivalent ways to do the same thing. Okay. So I have this one. what I know? I know this one. I know this one. I want this one. So it means that to have a knowledge about this one, okay, so I can write that P of the intersection is equal to P of A plus P of B minus P of the union. In general, it's not this way. We use this result, we use this formula in general, but we have this. So I have this one, okay? I know the sum of the two here. I have 3 over 4 plus 1 over 3. So it is, I put everything over 12, okay? So I have 13 over 12 for this one and for this one. I can say nothing about my statement, okay? I have nothing with the union, but I know that I have a probability here. Okay, I have a probability. So if I want the maximum of this number, I want to be greater than, I have to take so what can I say about this probability here? It's a proba, so it is between 0 and 1. So it belongs to the interval 0, 1. So when you do the sum of one number minus an element that in 0, 1, it will be greater for sure than what happens if I take the maximum for this value here, that is 1. Okay? So I have this one. And I repeat that when I see this statement, the first question is, I need to make the link between A, B, A intersected with B. So for this one, that's basic because I have one inclusion that I can use. Okay. The other is to say, okay, what happened in the unique formula I have in my course? That is this one. And to conclude, just say that I have probability here. So a probability is a number between 0 and 1. Okay, so if you have a number minus a probability, it will be greater than this number minus 1 for sure. Because my proba is always less than 1. Okay, always less than 1. So you have this. Okay? And I repeat that here, I have done no hypothesis on independence, on 1 is included. Okay, so it's not possible for you to solve this one, okay, if you take a very particular example, because I want the result in great generality. So it's possible to do a picture if it may help you, but you have to take a general picture. That is a case where A intersected with B is a priori, okay, not empty. And this picture won't help you in this particular situation. So I repeat, so I have given you this way to do, but you can do it using the idea of your friend here, and it gives rise exactly to the same thing. And it's that natural because this relation is the relation I have used in the course in order to prove this one. Okay? Okay, so I have done the exercise 6. Okay, for the next session, you will do this one, okay, at home. A very, very basic exercise. Okay, that is the exercise 13. I want you to do this. Exercise 13 for the next session, okay? So when I see this, okay, 2 words from my course, I can say. So I want to plant 2 types of plants in my garden, okay? I have type A and type B, okay? And suppose that both types will either yield red or blue flowers. We know some things. And the probability to be red given A is 0.4. The probability to be red given B is 0.3. My question, what is the percentage of red flower? And then suppose the red flower is picked randomly in my garden. What is the probability of the flower being type A? 2 words, if you have understood this exercise. For the first question, one proposition of the course, which one? No? When you see this, you have, okay, not sum of probability, because, okay, we work with conditional probability. We won't have disjoint sets here. So flowers are of two types, A or B. In my course, I have taken an example of an item that was, okay, made by 3 different factories and so on. It's exactly the same situation. To compute the first law of total probability, because being of type A or being of type B is a partition of the universe. Law of total probability. I think we finish, in fact. Huh? If you have understood this, the exercise is just write the law of total probability. Question B. So you will, okay, when I said, please, 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 I said when it is finished. You don't have class after, okay, I know this, and I have, so don't worry, okay, I need a break because I have 3 hours course after you, okay? But just finish this one in order to help you to do at home. For the question B, what I have in the statement, the probability to be red given A. What I want you to compute in the question B, the probability to be A if I am red, given that I am red. What is the relation in the course that helps you to do this? Bayes formula. Okay, so first question, law of total probability. Second question, Bayes formula. And in fact, you have nothing to do at all. Okay? So see you on Thursday. Bye-bye.